Question 4. Radium-226 decays into radon-222 by emitting an alpha particle. The table below has the nuclear mass of each part. Write a decay equation for this process. So we've got 226 radium with a proton number of 88 turning into radon, which has a proton number of 86 and a mass number of 222 and an alpha particle. Use the information in the table above to find the binding energy of radium-226. So if we want to do this in a single line, we need to find the mass defect, and multiply it by c squared. This needs to be in units of kilograms in order for it to work properly. So we're doing multiple sort of steps in one here. So what I'm going to do is get the value of delta M inside a square bracket. But first, inside the curly bracket, we're going to find delta M in units of U and then convert it. So the radium-226 contains 88 protons. Protons have a mass of 1.007276 in U, plus 226 minus 88 neutrons, so that's 138 neutrons, 138 lots of 1.008664. Take away the mass of the radium nucleus, so that's 225.977. So that's the close of our curly brackets. Then we need to multiply that by 1.66 times 10 to the minus 27. That closes our square bracket. So that's delta M in the correct units. And then we need to multiply that by 8.99 times 10 to the 16. So that's our calculation still on a calculator. Take away 225.977. So if you're working out as we go along, the mass deficit, so inside the curly brackets, should be about 1.85 U. So then if we convert that into kilograms, that gives us about 3 times 10 to the minus 27 kilograms. So that's when we do this multiplication here inside the square brackets, and then we're going to multiply that by 8.99 times 10 to the 16 to give us a binding energy of 2.77 minus 2.77 times 10 to the minus 10 joules. Next part, the binding energy of radon-222. So exactly the same idea applies. E is equal to minus delta M C squared. So this is minus square brackets in which I'm going to get delta M, curly brackets in which it's going to be in the wrong units. So I've now got 86 protons, 1.007276, plus it'll be 2 less neutrons, won't it, than last time, 136 lots of 1.008664. Take away the mass of the radon 221.970. Close the curly brackets, multiply by 1.66 times 10 to the minus 27 to convert into kilograms, close the square bracket, so that's delta M in kilograms. I need to multiply by c squared, 8.99 times 10 to the 16. So again, that's 86 lots of 1.007276 plus 136 lots of 1.008664. Take away 221.970. gives us a delta M in units of U of 1.83. That's inside the curly brackets. Then we're going to multiply by 1.66 times 10 to the minus 27 to get us a delta M in kilograms of 3.04 times 10 to the minus 27, and then multiply that by 8.99 times 10 to the 16 to get the energy as minus 2.74 times 10 to the minus 10 joules. So we've got the binding energy. Let's put some suffixes on these so we know what we're doing, of radium, the binding energy of radon, and then our last one, the binding energy of the alpha particle. So again, minus delta M C squared. So that's minus. So this time we've got 2 protons, so that's 2 lots of 1.007276 plus 2 neutrons, 1.008664, minus the mass of the alpha nucleus, 4.00151. Close the curly brackets, so that's where we worked it out in U. We multiply it by 1.66 times 10 to the minus 27 to turn it into kilograms. Close the square brackets and multiply by C squared, which is 8.99 times 10 to the 16. So again, same calculation, 2 lots of 1.007276 plus, let's not make a mistake, plus 2 lots of 1.008664, take away 4.00151, gives us the excess mass of, in units of U, 0.030. Then we need to multiply that by 1.66 times 10 to the minus 27. So 5 times 10 to the minus 29 in kilograms, and then multiplied by 8.99 times 10 to the 16 to turn it into 4 minus 4.53 times 10 to the minus 12 joules. So that's the energy of our alpha particle. Use your answer to B to estimate the energy of the alpha particle as it is released from the nucleus. So we're looking for the differences in energy, in binding energy in this part. So it's helpful to notice that we go from radium-226 to radon and the alpha particle. So what we want is the energy of the radium as a positive, and then we want to see the difference between that and the energy of the two things that are produced. So that's the energy of the radon plus the energy of the alpha particle. So that's the change in energy of the whole system. So this is minus 2.77 times 10 to the minus 10 minus the energy of the radon, minus 2.74 times 10 to the minus 10, plus the energy of the alpha particle, minus 4.53 times 10 to the minus 12. So I should say the binding energy of the alpha particle, because it's going to have its movement energy as well. And let's do the difference between those. If we just do it, if we got rid of all the powers of 10, we'd make our lives easier. So I'm going to get rid of that, and change that one to a 2. Don't like it when it does that. I want to get rid of the 1, but I'm going to keep the 2, and this is all times 10 to the minus 10 then. So minus 2.77 minus, open brackets, minus 2.74 plus minus 0.0453. Close the brackets. That gives us a value of 1.53 times 10 to the minus 12. So that's when I bring that power of 10 back in as well. So that is the excess energy that we've got left over. The binding energy difference between the two gives us the energy that we think the alpha particle should have. So 1.53 times 10 to the minus 12 joules. If we wanted to convert this into mega electron volts, we divide it by 1.6 times 10 to the minus 13, which would give us a value. We'd multiply it by 1.6 times 10 to the minus 13. Let's get that part right. No, we wouldn't. We'd divide. I'm doing the wrong thing. Let's try that again. Which would give us a value of 9.56 mega electron volts. So we probably